Acids and bases. Bronsted-Lowry theory. Weak acid. This is a substance that partially ionizes in water. This chart is on figure 14.3 in Brown and Lemay, 2nd Australian edition. This chart shows select acids and its conjugate bases and the relative strength of these representative substances. On the left, note the strength of acids decrease from top to bottom. On the right, note the strength of bases decreases from bottom to top. In the middle, a weak acid gives a weak conjugate base. Note the extremes. On the top left are the very strong acids. They give very weak conjugate bases that are negligible as bases. On the bottom left is the very weak acids. These are negligible acids, and they give very strong conjugate bases. Here are two examples of acids. The first is a strong acid, and the other is a weak acid. The strong acid is sulfuric acid, and the weak acid is carbonic acid. Both dissociate in water. Notice the difference in the way the chemical equations are written. Strong acids dissociate 100%, and the arrow is a single arrow that points to products. The weak acids are in equilibrium with its conjugate base, and the arrow points in both directions, and there are two arrows to represent this. Recall in equilibrium, we can determine the direction which is favored. Also note that dissociation is the same thing as ionization. For weak acids, because they are in equilibrium, we could write the equilibrium expression. K is equal to the concentration of hydronium ion times the concentration of hydrogen carbonate ion, divided by the concentration of carbonic acid. The products' concentrations are on the numerator, while the reactants' concentration are on the denominator at the bottom. And note that water is a solvent and a liquid, so its concentration is omitted or equal to 1. For acids, K is Ka, and Ka represents acid dissociation constant. Large Ka values favor the products. Weak acids have low Ka value much less than 1. The Ka of carbonic acid is 4.47 times 10 to the minus 7. In this example, let's compare the strength of two weak acids with their Ka values. Hydrogen cyanide dissociates or ionizes in water to give its conjugate base the cyanide ion and hydronium ion. The equilibrium expression is shown here, and the Ka value is 4.9 times 10 to the minus 10. Hydrofluoric acid dissociates or ionizes in water to give its conjugate base the fluoride ion and the hydronium ion. The equilibrium expression is shown, and Ka of hydrofluoric acid is 6.8 times 10 to the minus 4. Which of these two acids is stronger? Which is the stronger acid? Ka of HCN is equal to 4.9 times 10 to the minus 10, and the Ka of HF is equal to 6.8 times 10 to the minus 4. Notice that in order to answer this question, you don't need to write the chemical equation or the equilibrium expression. But for convenience and to reduce confusion with these exponents, we like to use manageable numbers. So chemists use the Pka scale. The Pka is equal to the negative log Ka. So for HCN, Pka is equal to the negative log 4.9 times 10 to the minus 10 is equal to 9.38. For HF, the Pka is equal to the negative log 6.8 times 10 to the minus 4 is equal to 3.16. Which of these two acids is stronger? Let's review this. Ka of HCN is much smaller than the Ka of HF, so the larger Ka gives the stronger acid. So this means that the ionization or dissociation of HF is greater than that for HCN. What? Confused? Then let's use pKa values by converting the Ka using pKa is equal to negative log Ka. The pKa of HCN was found to be 9.38 and HF is 3.16. So HF is the stronger acid. The lower pKa gives the stronger acid, and the stronger acid will have more ions as product. It is more ionized or dissociated. To calculate the pKa on your calculator, press the minus, then the log, and number 6.8, then press the EXP button, then -4. The EXP button is the power of 10. This is on your sharp brand calculators. To determine the Ka from pK is also possible. For example, the pKa of hypochlorous acid is 7.42. In order to calculate the Ka is equal to 10 to the power of minus pKa. For hypochlorous acid, the Ka is equal to 10 to the power of minus 7.42 is equal to 3.8 times 10 to the minus 8. There are two ways to determine this on your calculator. The first way, press 10, then press the button Y to the X. The calculator will display 10 to a power. This 10 is the Y. Then press the negative pKa. This will be the X. The second way is to use the inverse log. This is done by pressing the second F or shift on other calculators, then log. The calculator will display 10 to the power. Let's review acid and its conjugate base pair. For example, the acid is HF, hydrofluoric acid, in water to give the conjugate base fluoride ion and the hydronium ion. The acid is HF, the conjugate base here is F-. Now the base and its conjugate acid pair in this example is water is the base and the conjugate acid is the hydronium ion H3O+. Determining the direction of competing acids. Where an acid reacts with a base other than water, the conjugate acid and the conjugate base are not always on the product side. In this example, HCN, hydrogen cyanide, reacts with fluoride ion to give the cyanide ion and HF, hydrofluoric acid. To determine the direction of the reaction, evaluate the pKa. HCN has a pKa of 9.38 and HF has a pKa of 3.16. The low pKa gives a stronger acid and the reaction goes from low pKa to high pKa. The conjugate acid and the conjugate base are found on the left side or the reactant side. Determining the direction of this reaction or any equilibrium reaction can be mathematically done, but this is not for Chem 110.